Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This is another video in my series on graphing polar functions. In this video, we're going to focus on probably, I would say, the hardest style of functions to graph by hand. Most of the stuff that you're going to graph with polars will likely be beyond the scope of being able to graph by hand. This is the edge of that scope of graphing by hand. And these involve trig functions of multiple angles. So sine of b theta, where b is non-unit or not equal to 1. And so in this case, we're only going to do integer values of b. So like 1 or 2, 3, 4, 5, that type of thing. And this causes a little bit of an issue when it comes to graphing because there's a lot of work to do when you do this. So heads up, we're going to spend a little bit of time in this video doing that. Still, the method that I use to graph these is the same method that I've been using throughout all the videos in this series. If you haven't seen my general idea behind graphing polar curves video, I highly recommend that you do so you can see why I graph the way that I do. These are curves that I think are better memorized than they are actually derived, but let's go ahead and see how they're derived. As usual, we'll go ahead and just write out the Cartesian version or the rectangular form of this equation. So it's y equals 4 sine of 2x. And now I will graph that, which is a sine function that moves twice as fast as it normally would. So I have graphed this out. Notice that I have 2 cycles of the sine curve within this range from 0 to 2 pi. Remember, the maximum is 4 here and the minimum is -4. And that 2 cycles, you do have to actually graph from 0 to 2 pi because it does significantly change the graph of the related polar function. So I'll go ahead over off to the right here. Maybe actually I'll do it down because we need a little more room for this style of graph. I'm going to put a pole here and then we'll graph in the polar axis. So let me do that. And I'm just giving myself some extra room to work here. So let's see. When the angle is 0 radians, I'm throwing, so if you haven't seen any of my videos, this is going to make no sense to you, but when I am at 0 radians, I drop a stone at my feet, right? So I will go ahead and at 0 radians, when I'm facing completely to the right, I will just drop a stone. There we go. Now, I'm actually going to go ahead and rather than talk my way through all of this, it is true that as I increase the angle from 0 to pi over 4, the stones get thrown further and further away. I'm just going to directly get to pi over 4. So when I'm facing the angle of pi over 4, the stone is 4 units away from me. So let me go ahead and actually I'm going to use a ruler for this. And let's decide on a scale for this. So let's say that each of these pips is a distance of 1. And so when I'm facing an angle of pi over 4, which is 45 degrees, let me just move to 45 degrees here. We are throwing a stone 4 units in front of us. So that would be 1, 2, 3, 4 units right there. And I have the wrong color pen, of course. So there we go. And so between the angle of 0 and the angle of pi over 4, which is 45 degrees, we had these stones that were being thrown out further and further away as we rotated. So it kind of looks like this. And that is the path that we were throwing stones through. Now, take a look back here. And if we keep turning, by the time we get to face the angle of pi over 2, we're dropping a stone back at our feet. In the meantime, as we are turning, the stones get closer to our feet. So if you can imagine it, again, going back here, if you can imagine on this ruler, as I turn the ruler, let me see if I can keep that anchored, the stones get closer and closer to my feet until when I'm standing or looking straight to the angle of pi over 2, the stone gets dropped at my feet. So let's go ahead and graph those in here. So it kind of looks like this. Again, that was when we were at pi over 4. And then as we kind of turn here, by the time we finish the turn, the stones get dropped back at our feet. So it kind of does this path right here. And you can see this is significantly different than all the other graphs we've done so far. Now, go back up here and continue turning. And if you turn all the way to an angle of 3 pi over 4, which is halfway through quadrant 2, you're throwing stones behind you the entire time. So by the time you're facing an angle of 3 pi over 4, if I said 3 pi over 2, I meant 3 pi over 4, at a 45 degree angle here, you're throwing stones behind you the entire time. So by the time I'm facing this direction, the stones are 4 feet behind us. So let's go ahead and mark that out. 1, 2, 3, about right here. Okay. Again, so as we're turning, we move this off, otherwise it'll attract my pen. So we face this way, we throw something behind us. We face this way, we throw something behind us. We face this way, and it's all the way back there. So the way that the turns get carved out looks like this. So it's really hard to see this actually get graphed out like that, but it totally does. And then we go ahead and continue forward and worry about turning past the angle of 3 pi over 4, and we're still throwing stones behind us, but eventually they land at our feet by the time we're facing an angle of pi. So again, we were facing this direction right here, and we were throwing stones directly behind us. And as we continue to turn, we'll continue to throw stones behind us, but eventually by the time we face the angle pi, they're back at our feet. So they look like this. So again, imagine that you're facing in this direction and you start turning and you throw a stone behind you and behind you and behind you and behind you, and then finally at your feet by the time you face the angle of pi. Halfway through, right? We've made it halfway through this curve. And that's why I say these curves, the multiple angle curves like this, are generally harder to draw. All right, let's continue forward. As you increase past the angle of pi, all of a sudden, thankfully, we're throwing stones in front of us. And by the time we face the angle of 5 pi over 4, which is in quadrant 3, we're throwing a stone 4 feet in front of us. So let's go ahead and see that turn. So we're facing an angle of pi, and then we turn. And by the time we're facing the angle of 5 pi over 4, which is right about there, we have a stone 4 feet in front of us. So let's go ahead and plot that stone 4 feet in front. 1, 2, let's see, 1, 2, 3, 4, right there. Okay, so as we turn, we're throwing stones in front of us, just like that. So something like that. Again, just like this right here. And then as we continue turning and we eventually face the angle of 3 pi over 2, the stones are back at our feet. So we decrease the distance as we continue turning. So you're going to continue turning and eventually those stones will be back at your feet. So let's go ahead and just continue the turn here. Throwing a stone forward, but eventually they get back to our feet. So just like that. You have to be good at thinking spatially here to do these appropriately. And then you can kind of see that there's a symmetry here. So it's sort of a, not a cheat, but a use of symmetry to say, okay, well, as I turn past 3 pi over 2, and once I get to 7 pi over 4, I'm throwing directly behind me 4 feet. And that would be this. So you're facing this direction, but you're throwing behind you 4 feet. Let's get that going correctly. So here we go. And let me get the right pen. 1, 2, 3, 4 right there. And the entire turn you're throwing behind you. So something like this. Oops, a little bit too wide there. Sorry about that. So something like that. And you can kind of see it's going to loop back here. So there you go. That is the full graph. I didn't bother talking our way through the last piece there, but that is the full graph. Turn off my ruler here. And note, it was a sine of 2 theta, and we end up with 4 leaves on this rose. We call this a rose, and it's a 4-leaf rose, and there is something very special about that. But that's the basics of how you would graph a multiple angle formula. In fact, that's how you could graph any of the sine or cosine functions like that. You just, draw this out and measure. Now, like I said, these are this is the worst case scenario. You don't really want to constantly draw these by hand. So you eventually want to just know what they look like in general. And so it's good to know when you have a multiple angle formula for the sine or the cosine in polar coordinates, it's going to be a multiple leaf rose. Now you would think that with sine of 2 theta being 4 leaves, that maybe the sine or the cosine of 3 theta would be 6 leaves, but that's actually not the case. Let's go ahead and take an example of that just to kind of drill the point home here. It is something to do with the fact that that number, the angle, the 3 there on the number, or 3 on the angle, is odd. When it's odd, you get the same number of leaves. So we'll get a 3-leaved rose here. When it's even, it's twice the number of leaves. That's all. But let's go ahead and start to graph this. Graph the rectangular form of it. So y is equal to 5 cosine of 3x. And I'll quickly just pause the video and graph that out. Now this is a pretty gnarly graph just because it's so many oscillations between 0 and 2 pi, and you need all of your graph between 0 and 2 pi. So there's a lot of discussion going on here. And this is why these tend to be on the cusp of where you should probably start memorizing graphs, because these ones right here are just a bear to graph out by hand. I really dislike them myself. So let's go ahead and start with a pole, and we'll draw in a polar axis. And now we're going to go to our graph here, and probably the best thing to do is to go ahead and plot points. That might be the easiest thing to do. So for example, at time 0, or sorry, theta equals 0, in this case it's x, but that's okay. When our angle is 0, our output is 5. In other words, we throw a stone 5 units away. So let's go ahead and do it that way. Let's just plot points, and then we'll come back and figure out what things are. So I'm going to measure out 5 here. 1, 2, 3. Wait, 1, 2, 3, 4, 5. So this is 5 units right out there. Oops. I got to get this a little bit further away. There we go. All right. So that's 5 units away. Now let's go ahead and see what the next point is. When we face the angle of pi over 6, we drop a stone at our feet. And that's the problem here, is that this is such a coarse step. Like, it's hard to say, like, well, when I'm facing an angle of pi over 6, which by the way is 30 degrees, I drop a stone at my feet. Like, that doesn't really give us very much, does it? Like, what happened in between that? That's why I'm saying, like, it's a little bit coarse. But the reality is, what happened between that was that we had distances that were shrinking. And so we'll have this curve, as we open this angle, shrink very quickly to this. So we'll get this pattern going at the very least. Let's see. Then by the time we're facing an angle of pi over 3, we're throwing a stone behind us 5 feet. So let's go ahead and face an angle of pi over 3, which is 60 degrees. Let's go ahead and do that. I'm almost there. I don't know why it's not turning completely. There we go. I just had it. 60 degrees. There we go. 60 degrees. And we'll throw a stone behind us. So in the opposite direction, 5 feet. So 1, 2, 3, 4, and 5. I think that's 5. Yeah. And the entire time, let me move this off to the edge, otherwise it'll get in my way for the rest of this problem. The entire time, as we're turning, the stone is being thrown behind us. So it kind of looks like this. Let's see if I can zoom out a little bit. So this is what we get. I kind of just paused the video and went ahead and drew that out very quickly. The one thing that you should notice, the path is going to be smooth. The path of travel here is not going to be a jagged kind of quick turn. It's just a nice smooth travel for this particle is what we would call it. Anyhow, going back, let's see. So we threw rocks behind us until we got to that. As you turn to an angle of pi over 2, you keep throwing rocks behind you until they land back at your feet. So again, by the time I complete this turn to pi over 2, which is 90 degrees, we will have stones land at our feet. So showing that movement, it goes like this. So I will actually just showcase that movement here. So it does something like this. Turns this corner and goes this direction, and the stone lands at our feet. And then, increasing past an angle of pi over 2, we start throwing stones in front of us until when we're facing 2 pi over 3, which is 120 degrees, we throw a stone 5 feet in front of us. So when we face an angle of 120 degrees, we throw a stone, 5 feet in front of us. Let me zoom in and get this as accurate as possible, just so this looks right. So there we go to there. And you kind of see the pattern, the rows kind of start forming there. And then coming back here, as we move past that and move to 5 pi over 6, we then decrease those distances, and at 5 pi over 6, we drop a stone at our feet. Now 5 pi over 6 is going to be roughly around here. Whoops, very roughly. So that's the angle we're facing, and by the time we face that angle, we drop a stone at our feet. So the path of travel for this particle will look like this. It's just doing this. Sorry for my sketchiness here, but this is the path of travel, if you can see those arrows. And then we drop a stone at the feet, and from that point forward, starting at 5 pi over 6 and going facing angle pi, by the time we face the angle pi, we have a stone 5 feet behind us. So again, we're facing this angle right here. And then as we turn, we throw stones behind us until they are 5 feet behind us right here. Now something special happens at that point. So throwing stones behind us, they will go there. And the specialness that happens at that point is the route is completed. We have completed the path. So in reality, we didn't need all of this. If you continue graphing, it'll just retrace itself. And so this becomes just a nice 3-leaved rows. There's nothing new to it from this point forward. It'll actually just continue this pattern. You could try it out, but if you notice, it should begin. You could try it though. Let's just see. So if you go past pi over 2 and you get to 7 pi over 6, you're throwing a stone behind you. So in other words, you start at, I said pi over 2, but at pi, you start by facing pi, and as you turn this direction, you're throwing stones behind you, and you can see that you will be tracing out that very same curve. So it is the same curve no matter what. So you know what I'm going to do here? I just want you to see the path of travel for a particle. So I want to show you how to use Desmos to visualize the path of travel. In fact, you know what? I'm going to add a video to this series called the Desmos and let's say graphing polar curves or something like that, just so you could see that. No, I'll go ahead and just do it right now. The first thing I want you to notice here is that this is the graph of 5 cosine of 3 theta, and yeah, it looks identical to what we graphed. So it's perfectly fine to have this beautiful looking graph. I'm going to zoom in a little bit, but I also want to show you how to show the path of travel. So to do this, what we're going to do is create a point. And to create a point in Desmos, you would just do something like x comma y, right? That's a point. The problem is that in polar coordinates, it's not x comma y. The x values are r cosine of theta and r sine of theta. If you want to get a theta, just type it out, theta. theta, and then y is equal to r sine of theta. But the problem here is I want to showcase it tracing out, so I'm going to say r sine of a and r cos of a. But even then, I can't, that's not going to do it for me because I need to know what r is. I know we labeled r here, so maybe I should say r of theta just so that it knows that I have a function of theta. And I'm going to call this r of a times cos of a and r of a times sine of a. That might work. Let's just see. Yep, that'll work. Okay, so I'm going to have a go from 0 to 2 pi. And you don't really need to know how to do this, so it's okay if you don't know how to do this, but I would like to show you. You can always rewind the video and see how I did this, but the reality is we know that the x value is always r cosine of a, the y value is always r sine of a, or r cos theta, r sine theta, but I want to showcase what the point looks like as theta gets larger. So I'm letting theta equal a, and I'm now going to press play by slowing this down a little bit so you can see the path of travel. It's very beautiful, and this is actually the path of travel that we graphed out. Very neat, right? And if you want, you could change your function to be something else. By the way, it hasn't even got to 2 pi. It's already traced out a full cycle. Now it's going through its second cycle all the way to 2 pi. Now I'm going to back that up, and I'm going to change my function to the first function we had, which I think was a sine of 2, right? And if you press play, you'll see it carves it out. And as it gets to, so here's the second part of it right here, it's almost to pi. There we go, that's pi. And then from this point forward, it carves out the left side of it. So when you have an even number on that, you from 0 to 2 pi, you need the entire graph. But when it's an odd, you only need half the graph. So anyhow, you can play around with this all day long. So if you want to go to 12 pi, for example, you get a 24 leaf rows. And if you press play, you could see how it gets carved out. Now, I would not want to graph that by hand, and I would never give that to my students to graph by hand. That's just terrible. But anyhow, some beautiful things that you might be able to see with polar curves is that they have some beautiful ability to be, they just have some beautiful curves to them. So anyhow, I'm now fascinated with watching this go. We'll just stop the video now as this plays.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.